A rotary kiln is a pyroprocessing device used to raise materials to a high temperature in a continuous process. Materials produced using rotary kilns include cement, lime, refractories, metakaolin, titanium dioxide, alumina, vermiculite, iron ore pellets. They are also used for roasting a wide variety of sulfide ores prior to metal extraction. Principle of operation: the kiln is a cylindrical vessel, inclined slightly to the horizontal, which is rotated slowly about its axis. The material to be processed is fed into the upper end of the cylinder. As the kiln rotates, material gradually moves down towards the lower end, and may undergo a certain amount of stirring and mixing. Hot gases pass along the kiln, sometimes in the same direction as the processed material, but usually in the opposite direction. The hot gases may be generated in an external furnace, or may be generated by a flame inside the kiln. Such a flame is projected from a burner pipe which acts like a large Bunsen burner. The fuel for this may be gas, oil, pulverized petroleum coke or pulverized coal. Construction: the basic components of a rotary kiln are the shell, the refractory lining, support tires and rollers, drive gear and internal heat exchangers. History: the rotary kiln was invented in 1873 by the Englishman Frederick Ransom. Kiln shell equals, this is made from rolled mild steel plate, usually between 15 and 30 mm thick, welded to form a cylinder which may be up to 230 meters in length and up to 6 meters in diameter. This will be usually situated on an east-west axis to prevent eddy currents. Upper limits on diameter are set by the tendency of the shell to deform under its own weight to an oval cross-section, with consequent flexure during rotation. Length is not necessarily limited, but it becomes difficult to cope with changes in length on heating and cooling if the kiln is very long. Refractory lining equals, the purpose of the refractory lining is to insulate the steel shell from the high temperatures inside the kiln, and to protect it from the corrosive properties of the process material. It may consist of refractory bricks or cast refractory concrete, or may be absent in zones of the kiln that are below around 250 degrees Celsius. The refractory selected depends upon the temperature inside the kiln and the chemical nature of the material being processed. In some processes, such as cement, the refractory life is prolonged by maintaining a coating of the processed material on the refractory surface. The thickness of the lining is generally in the range 80 to 300 mm. A typical refractory will be capable of maintaining a temperature drop of 1000 degrees Celsius or more between its hot and cold faces. The shell temperature needs to be maintained below around 350 degrees Celsius in order to protect the steel from damage, and continuous infrared scanners are used to give early warning of hot spots indicative of refractory failure. Tires and rollers equals. Tires, sometimes called riding rings, usually consist of a single annular steel casting, machined to a smooth cylindrical surface, which attach loosely to the kiln shell through a variety of chair arrangements. These require some ingenuity of design, since the tire must fit the shell snugly, but also allow thermal movement. The tire rides on pairs of steel rollers, also machined to a smooth cylindrical surface, and set about half a kiln diameter apart. The rollers must support the kiln, and allow rotation that is as nearly frictionless as possible. A well-engineered kiln, when the power is cut off, will swing pendulum-like many times before coming to rest. The mass of a typical 6x60m kiln, including refractories and feed, is around 1100 tons, and would be carried on 3 tires and sets of rollers, spaced along the length of the kiln. The longest kilns may have 8 sets of rollers, while very short kilns may have only 2. Kilns usually rotate at 0.5 to 2 rpms, but sometimes as fast as 5 rpms. The kilns of most modern cement plants are running at 4 to 5 rpms. The bearings of the rollers must be capable of withstanding the large static and live loads involved, and must be carefully protected from the heat of the kiln and the ingress of dust. In addition to support rollers, there are usually upper and lower retaining rollers bearing against the side of tires, that prevent the kiln from slipping off the support rollers. Drive gear equals, the kiln is usually turned by means of a single girth gear surrounding a cooler part of the kiln tube, but sometimes it is turned by driven rollers. The gear is connected through a gear train to a variable speed electric motor. This must have high starting torque in order to start the kiln with a large eccentric load. A 6x60M kiln requires around 800 kilowatts to turn at 3 RPMs. The speed of material flow through the kiln is proportional to rotation speed, and so a variable speed drive is needed in order to control this. When driving through rollers, hydraulic drives may be used. These have the advantage of developing extremely high torque. In many processes, it is dangerous to allow a hot kiln to stand still if the drive power fails. Temperature differences between the top and bottom of the kiln may cause the kiln to warp, and refractory is damaged. It is therefore normal to provide an auxiliary drive for use during power cuts. This may be a small electric motor with an independent power supply, or a diesel engine. This turns the kiln very slowly, but enough to prevent damage. Internal heat exchangers heat exchange in a rotary kiln may be by conduction, convection and radiation, in descending order of efficiency. In low-temperature processes, and in the cooler parts of long kilns lacking preheaters, the kiln is often furnished with internal heat exchangers to encourage heat exchange between the gas and the feed. These may consist of scoops or lifters that cascade the feed through the gas stream, or may be metallic inserts that heat up in the upper part of the kiln, and impart the heat to the feed as they dip below the feed surface as the kiln rotates. The latter are favored where lifters would cause excessive dust pickup. The most common heat exchanger consists of chains hanging in curtains across the gas stream. Other equipment: the kiln connects with a material exit hood at the lower end and to ducts for waste gases. This requires gas-tight seals at either end of the kiln. The exhaust gas may go to waste, or may enter a preheater which further exchanges heat with the entering feed. The gases must be drawn through the kiln, and the preheater fitted, by a fan situated at the exhaust end. In preheater installations which may have a high pressure drop, a lot of fan power may be needed, and the fan is often the largest drive in the kiln system. Exhaust gases contain dust and there may be undesirable constituents such as sulfur dioxide or hydrogen chloride. Equipment is installed to scrub these out before the exhaust gases pass to atmosphere. Thermal efficiency: the thermal efficiency of the rotary kiln is about 50 to 65%. See also, List of ovens. Sources and further reading: R. H. Perry, C. H. Chilton, C. W. Green, Perry's Chemical Engineer's Handbook, McGraw-Hill, Sections 12.56-12.60, 23.60, ISBN 978-0-07-049841-9, K. E. Perry, The Rotary Cement Kiln, CHS Press, ISBN 978-0-8206-0367-4, Boateng, Accorsi, Rotary Kilns, Transport Phenomena and Transport Processes. Amsterdam. Boston, Elsevier Butterworth Heinemann, ISBN 978-0-7506-7877-3. References